about. By the way, today I have a different computer to work with. My regular computer is not available to me today, so I'll not be able to write anything. So we will have to go to the slides. I'll try to write a few things wherever I have to, but I'll try to minimize that writing effort. Yeah. So please bear with me. So in the previous class, we had talked about composite beams primarily, right? So any questions with on that topic, composite beams? You guys understood, followed the subject? How many of you went to my website and tried those worksheets to calculate the design of a composite beam? Nobody? Nobody wants to say it here. Okay. I would encourage you to. So, I mean, you must be browsing internet all the day, right? So, yes, you can try to go to my website and try that link. So, this will give you some idea about, because it gives you an option of non-composite action versus composite action. So, you pick a beam and then you go for non-composite action. That means you are not providing the shear studs, and then see what size, whether that beam is satisfying this load requirement. Then you say composite action, and then you see which size beam is adequate. So that will give you some idea about, or also it gives you factors of safety. So it will tell you, okay, this is the factor of safety for composite action, and this is the factor of safety without composite action. So that in a way gives you some indication of what is a better, like why composite beams are more efficient designs. Of course, it takes a lot of effort. I have not gone into the detail of how these shear studs are installed and what are the options available instead of shear studs. So shear studs are not the only solutions, these shear connectors. So there can be various kinds of shear connectors. Another type of shear connector which is very commonly used are channel sections. So you take a channel, C section, and you cut into small pieces. The pieces should be shorter than the width of the beam, so that it can very easily be welded to the top of the flange. And then you put those channel sections, weld them to the top flange, and then cast concrete. That thing also works equally well. These shear studs that they look like almost like a bolt. These shear studs are very, very effective, and they are much faster to weld. You can go to the internet and again try and see how they are welded. This welding process is very fast. Almost they are able to weld one shear connector within 10 seconds or something like that. And they already have a pre-marked locations. One person goes with a kind of a gun which has all the shear connectors stored, or I think he puts the shear connector from outside and just connects it, and immediately it gets fused through the steel deck and goes and fuses with the top flange. Okay. But there are other options other than these shear connectors. So not everybody has that kind of infrastructure. So sometimes they go with the regular traditional kind of arc welding, and then they use channel sections also. Okay. Of course, I have not discussed how to design composite beams in this course because it took so much time to explain the very, very basic concepts about yield point and failure theories and all those things. We will see, we will come back to this. So that's why I want you to go through those Google Sheets and try to understand what happens, how the behavior changes as you move from a regular beam or non-composite beam to composite beam. Okay. Moving forward, I hope there are no questions. Suppose, not hope. Yeah, no questions. Okay, moving forward. The next chapter within the next section within the flexural members chapter is the combined forces, right? So you may have combined shear and flexure acting together, which in fact acts almost always together. Yeah. So flexure, whenever it's there, it is almost always combined with shear in practical situations. On a theory, you can say that you may have pure flexure, but in reality, you will always have, through the length of the member, you will always have some shear somewhere. Okay, so in such conditions, we have already discussed how to design for flexure and shear combined. Okay, moving forward, when we talk about the possibility of combined axial and flexural loads. Okay, so when the axial load is acting with along with flexural loads, then the member is not a beam anymore. What is it now? It's a beam column. Okay, and column, if it is compression, if it's a tension, then I don't know what to call it. Yeah. So if it is compression in axial direction and flexure, that is bending moment, then you call it a beam column. Okay. And this is the more likely situation. Basically, typically your beams don't undergo very large compressive force. under earthquake conditions, there is some axial force acting on these beams, but even that axial compressive force is mostly carried by the slab, not so much by the beam. So beams don't usually, and plus beam connections are also not designed, the connections at the end of the beams are not usually designed to resist a lot of axial forces. So the beams are not really beam columns. Very rarely would you see a situation where beam acts as a beam column. Which is a beam column then? The columns are really beam columns. So columns are meant to be carrying only gravity loads or only compressive loads, but there may be situations when the columns which are supposed to carry only compressive loads are also subjected to bending moments. Which are those situations? Can somebody tell me a few situations when this may happen? When columns are subjected to bending moments?
Eccentric load.
Eccentric loading. Very good. Any other situation? Sorry?
Lateral forces.
Lateral forces. All kinds of lateral forces do that to the columns. Very good. Yeah. So these are the two primary conditions when you may have that kind of situation. Okay. So you must have been taught about interaction curve, PM interaction curve in RC column course, right? Yes or no? Yes. Okay. So the PM interaction curves were looking somewhat like this. You can see this geometry here. You can see this geometry here. So that's how the PM interaction curve used to look like. Maybe I can draw a quick one to refresh your memory. A typical PM interaction curve used to look somewhat like this, right? You used to have M on this axis and P on this axis, correct? And if you bring in, that might be M about one axis, then you may have M in other direction also. Then what you will get is basically this kind of an onion shape. Yeah? That is also known as onion bulb or onion or bulb shape or something like that. Yeah? PM interaction curve. You agree? This you're familiar with, right? All of you. So anyway, which basically this curve, what it says is that whatever your failure condition is, let's say you are saying that failure takes place when steel yields and failure takes place when concrete crushes in RC I'm saying. So basically those two limit states, when one of those limit states is met, that's when you draw this curve, right? So so when let's say you are at this point somewhere, so what happens at this point is that if you are inside this geometry, inside this bulb, then you are safe. As soon as you come and touch this boundary, that's when the limit state is reached. The exact same thing is true for this shape. So this shape you can see here. In this shape, you have M versus M and Z. M, so that is in Z axis. This one is in Z axis. This one is in Y axis. And this is the axial force. Okay. So what it is saying is that the limit of moment, the actual moment in the numerator, and the denominator is the capacity. Similarly, in y-axis, the actual moment versus the capacity, and the vertical axis is the actual force divided by the actual load capacity. And that relationship is given by this geometry. And as long as you are inside this geometry, so starting from the origin, as long as you are within this geometry, your column has not reached the limit state. The same equation, the same geometry is represented in equation form here. Yeah, so this equation you can see. This is that equation. Now in this equation, if you see, there is m divided by mn dy, okay, to the power alpha 1. And the values of alpha 1 and alpha 2 are given in the code. I have not written because these are long set of equations actually. And mz divided by mn dz to the power alpha 2, and that should be less than or equal to 1. Okay. Now you may see that this equation does not have a component of p. Right? What I'm saying is that even though p is there, the equation only has m and m components, right? So actually what is happening is that this m and dy that is one denominator, and M and DZ, that is the other denominator, both of them are calculated for only axial force and only bending moment acting in one direction. So basically what you did first you calculated M and dy and M and dz as if only M and dy is acting and axial force is acting, and when is the limit state. And there are equations given for that in IS 800. You have to go to 9312, clause number 9312 in the Indian code. There you will find the equations for M and dy and M and dz, okay, which depend on their respective critical buckling state. Sorry, this is not respective critical buckling. This is about the axial stresses. This is purely with respect to the cross-section stresses, okay? So which depend on their respective My value, yield stress, and MP values, plastic stress, plastic moment. So based on those, you calculate your M and dy and M and dz values, which already have the effect of P incorporated in these terms, okay? And then you divide actual M in that direction, Y direction, divided by the capacity, and actual M divided by the capacity, and that is this equation. Okay, and of course many of these parameters such as values of alpha 1, alpha 2, etc. are empirical, and we work with them. Alternatively, conservatively, so basically what this equation does is this equation allows you to go beyond the yield point, because we understand that yield point is not necessarily the limit state, right? The first yield, when the first yield takes place, that is not necessarily the limit state. Many members can sustain much later, much beyond the first yield. So therefore this equation allows you to use that, and that's why these shapes that you see are not straight lines, these are curved. Alternatively, a conservative approach is, which is what the code used to have before this revision, was this equation. Okay, so this basically equation is saying that the limit state is reached as soon as the first fiber yields. So what you're saying, your N divided by ND, that is basically the force divided by the axial load capacity of the member, which is basically P multiplied which is basically the moment capacity for yielding in one axis, and that MdZ is the moment capacity acting in the Z axis, okay, and that includes the LTB effect, lateral torsional buckling effect. So whatever the capacities are respectively in each axis, you divide them with the you divide the demand with the capacity in each axis, and then that should be less than or equal to 0, equal to 1. So when you do this, you get this kind of a geometry, which is like a pyramid, okay, and this basically is a conservative estimate. It limits the stress in the extreme fiber, whichever fiber is going to yield first, to be under the yielding point. So as soon as one fiber reaches the yield point, you say that that is the capacity. This is a conservative estimate. You are allowed to use this one. Many times I see people using this equation because this equation is a bit too cumbersome. So many design professionals use this equation, the second equation. Okay. Now, here the value of N can be in tension or as well as in compression. Yeah. The reason for that is because all you are doing is that there is certain stress because of bending, there is certain stress because of bending in the other direction, and there is certain stress coming in from tension or compression. So now if there is a bending in this direction, let's say in the major axis, so one fiber is in tension, the other fiber is in compression. So if there is a tension force applied, tension axial force is applied, then that will interact with the tension force. So that fiber will be about to yield. If compression force is applied, then that compression force will be interacting with the compression force, and this fiber will be willing to or going to yield first, the bottom fiber. So either way, one of the fibers is going to reach. So it doesn't matter whether the force is tension or compression, you just substitute the values here as it is. Yeah, and don't put the sign, and that value should be less than 1. Now this equation is very accurate for semi-compact sections, because in semi-compact sections, you are anyway not supposed to go beyond the yield point, because beyond the yield point, what do you get in semi-compact section? What happens in semi-compact sections after the yield, after the first yield?
Local buckling.
Very good. Local buckling takes place. So therefore, you can't really utilize beyond the yield point, because as soon as local buckling takes place, the entire capacity is gone. Very good. So these equations can be used for calculation of the section capacity. Yeah, but that is not necessarily the full story. The full story is actually, because you might have, all of you might have heard of term P delta effect. How many of you have heard of P delta effect? At least a few of you can say whether you have heard of P delta effect. P delta effect. Okay, at least one person has said. I'm asking this because I want to know whether I should explain the P delta effect fully or I can skip it. If you want me to explain the entire P delta effect, I'll do that. You want me to? People, please answer. Okay, fine. Okay, so P delta effect is also known as geometric nonlinearity effect. Yeah, you can see this landed geometric nonlinearity. Yeah. So I'll explain you this thing in. I can give you an easier example to understand P delta effect, but then since I'm limited in how much I can draw today, I'm trying to follow. Please try to follow this diagrams itself, whatever you can see on your screen. This MA, what it says is basically should have been M subscript A and M subscript B. The subscript has come down to the next line. So basically this is MA, M at A point and M at B point. So let's say you have a member, yeah, and the member is initially carrying some moment in this direction, some moment applied here. So as a result, you will get a bending moment diagram which looks like this. Yeah. So let's say MA is smaller than MB, so you will have a bending moment diagram which will look like this. And these moments could be coming due to lateral loads also, but I'm assuming that the moments are coming from externally applied moments. Okay. Now, as a result of this externally applied moment, the member would bend, right? So the member has bent, let's say, by a magnitude delta 1, that is maximum deflection. So delta 1 is the maximum deflection anywhere in this member because of the flexural action. Now what happens is that, let's say this member turns into a beam column. That means it has an axial force as well as the moments that were applied before. So now this additional axial force, it is not acting on a straight column. It is acting on a curved column, right? So that means on a curved column, when this force is acting, at this location, the axial force is P and there is moment MA at this location. I hope you can see, I cannot. At this location, the moment is MB and axial force is P. However, at this location, if you see, at this location, at the midpoint, that's where the maximum deflection is. What is the net moment? The moment was, earlier the moment was average of MA and MB or something in between, because the point of maximum deflection will not necessarily be right at the midspan. So wherever that is, this moment will be something in between MA and MB, linearly varying. But now what will happen is that because of this curved shape and this additional P acting, there will be a P multiplied by delta moment, right? So if I may draw, let me try to draw it here clearly. Try to make the point more vivid. So this is the original column and this is the deformed column. Then you have a P force acting here and here. Now, if I take half of that column, this part, if I take that part, and P is acting here, and that P has to be resisted like this, okay? And for the moment, forget how this curved shape took place. Assume that it was already curved, let's say, and this P is acting. Now, what will happen is that these two forces, P and P here, are not balanced. Force-wise, they are balanced, but moment-wise, they are not balanced. How will they be balanced? So these two P's want to make the member go in this direction, but you need a moment that will bring it back in this direction. So basically, there has to be a moment acting in this direction. Then only it will be in balance. And how much will that be? That will be equal to, if this distance is delta, that moment will be P times delta. Okay. Sorry for the poor quality of drawing. So the P delta moment that is happening here, that is an additional moment. It is also known as secondary moment. Yeah. So the primary moment was your MA and MB. Then you get a secondary moment of P delta. And for calculating this P delta, now what will happen is, because of the P delta, the bending moment diagram has changed. Earlier, the bending moment diagram was this. So you got this curved shape. The bending moment was, sorry, the bending moment diagram was this. So you got this curved shape. But now the bending moment diagram has changed to this. So the curved shape will change again. And the final new deflection will be delta 2. And because of delta 2, again the moments will increase and the new deflection will be, let's say, even larger. So basically it becomes an iterative procedure. If you want to do it numerically, then you have to do it in iterations until you find a convergence point. Okay, so that's why this is called geometric non-linearity. So this is geometric, and that's why it is called non-linearity, because what happens is that as you keep increasing your p-value, your lateral deflection does not vary linearly. It increases suddenly and then varies more rapidly than initial lateral deflection. So what will happen is delta 2 is greater than delta 1. This was your delta 1, this was your delta 1, and this is your delta 2. So delta 2 is greater than delta 1, and you do more iterations and you will find that you will get delta 3, delta 4, delta 5, and subsequent terms will be smaller and smaller, but summation of them will be larger. Okay, so that is what is known as geometric nonlinearity, and that also, so every time in steel, steel members are more susceptible to all kinds of buckling or all kinds of geometric nonlinearities. Okay, because our members are relatively more flexible than concrete RC members. So in order to account for that, there is another interaction equation that is given in clause number 9.3.2.2, which takes into account the possibility of lateral torsional buckling along with the geometric nonlinearity effects, right? So this P delta effect is accounted for. I'm not going to have time to explain this whole thing to you, but these two equations are available. This is a quite involved equation. So basically there is an amplification factor for each of these deflections. For Y, that is deflection in Y or the moment in Y. Z is for moment in Z. And even for lateral torsional, buckling can get amplified. So for that, there is KLT. In addition to that, since the moments will not be uniform through the length, we have discussed this factor before, wherein for lateral torsional buckling, we were using M critical equation that is given in section 8. But if you don't want to assume uniform moments, you have to go to annexure E. Same thing, here it is incorporated in case of beam columns, it is incorporated in the main code. So the main code has these correction factors CMY, CMZ, CMLT for non-uniformity of the moments. So if the moments are non-uniform, then you can account for that by using these C factors. I don't want you to completely by heart these equations. Of course, you don't have to by heart any of the equations that are there in the code, but also this is not really something that you will be using from day to day in your day-to-day life. But you should have an understanding that these kind of provisions are existing and why are they there? What is the purpose of this equation? That is what the purpose of this particular session is. Okay. So with this, I think also another thing I forgot. When we were dealing with section behavior, we were saying that you can substitute tension for compression. If you have tension load, you use the same equation. Don't use the sign of tension, a different sign for tension versus compression. You use the same sign, the behavior remains exactly the same. So in other words, when you saw this shape, the behavior on this side and the behavior on the opposite side are exactly the same. Similarly here, the behavior on this side and behavior on the opposite side are exactly the same. The behavior in tension and compression are not different. However, when it comes to this is the secondary moment effect, right? And secondary moment effect gets enhanced when you have compression. But what happens to the secondary moments when you have tension? So let's say I have a member and there is moment acting on this. And because of this moment, the member bends like this. And I have a delta 1. That is maximum deflection somewhere. Okay. Now, if I apply tension on this member, so this member is already curved this way. And if I apply tension, okay, because of this tension, what will happen to what will be the bending moment in the middle? What will be the bending moment at the middle? It will be T delta 1, correct? But if you notice, this T delta 1 will be in opposite direction of the moments that you had applied. So the secondary moment is still there, but secondary moment is acting against the original primary moments. Okay, so basically as a result, what will happen is that the new deformed shape will not be with after applying T, the new deformed shape will not be as deformed, it will be less than this. So the second iteration deformation will be less. The third iteration deflection will be a little less. And likewise, your deflections will reduce. So actually, tension along with bending moment, that does not diminish the strength as far as buckling is concerned. It may enhance the strength. As far as buckling is concerned, I'm not saying, because when you were looking at the stresses in the cross section, it was having the same effect as the compression force. But as far as buckling is concerned, tension can be more stabilizing. Tension can have more stabilizing effect rather than destabilizing effect. And therefore, the new moments demands can be calculated by taking the original capacity and subtracting the tension effect. Okay. So you can go through these equations and try to understand them. If you're not able to follow completely, you can ask me. I'm not going to talk about these equations in any more detail here. So with this, I'm concluding the chapter on flexural members. If anybody has a question, please feel free to ask me now.
Sir, in the interaction diagram, what is the difference between MNdy and Mdy?
So the question is, what is the difference? Let me erase all this, whatever I wrote, so that I can start afresh. So if I understood the question correctly, the question is, what is the difference between this MDY and this MNdy? Is that right?
Yes, sir.
Okay. So MDY is basically moment capacity in that axis as if no other force is acting. Okay. So moment capacity in y-axis when nothing else is acting, only moment is acting in y-axis. What is the moment capacity? And MNdy already has the effect of N. N here is axial force. Small n, that is same as this capital N. So that already has the effect of axial force. So basically, in order to get the value of MNdy, there is another interaction equation which takes into account the interaction of N, axial force, or in this diagram I'm calling it P. So axial, it takes care of the interaction between P or N, whatever one you want to call it, and the moment in that direction. So that's why this equation, if you see, does not have any terms corresponding to N. The second equation does have terms corresponding to N, but the first equation does not have terms corresponding to N, because that N effect is already there in the denominator. You got it?
Yes, sir. Thank you.
Okay. Any other questions? So I think I can move forward now. There is one example given in the lecture notes that is for a laterally restrained beam, which deals with the moment capacities and so try to calculate the moment capacity. So the cross section is a plastic cross section. So the calculations are pretty straightforward. There is not much complication here. It is checking for the shear capacity and whether the shear capacity is at least 60% more than the shear demand is at least less than 60% of the shear capacity. And since it finds that to be true, so there is no interaction between shear and flexure, and then it goes on to design the member for the or check the design for flexure. Okay, I suggest that you go through the steps here, go through the calculations, and make sure that you are able to understand everything. One check is missing here. That check I should have added, but I didn't have the time. Is the check for shear buckling. Yeah. So shear stress is anyway very low there, and this is I'm going with an ISLB section. ISLB section here, right? So whenever you are going with one of these ISLB hot rod sections, you won't have a risk of shear buckling. But anyway, I should have shown the calculations that shear buckling is not going to take place before yielding. So D by T W should be less than 67. That check is missing. That check you can add. When you solve the problem in the assignment or in the quiz or exam, you should check for that. Okay. So it's not a complicated problem, so that's why I'm not going into stepwise. So that will become boring for you. So you can go and check. If you have doubts, you can email me, I'll answer them. Okay. So can I move forward to the next chapter now? I'm taking that as a yes. So the next chapter is connections, or you can say bolted connections, and then the next subsequent chapter will be welded connections. So we are going to talk about what bolts are, and what are the different types of bolts, and how they are graded, and how to design bolted connections. Okay. So you all must have seen bolts, right? If I were in the class, I would have brought a bolt from the lab to show you how a typical structural bolt looks like. But I'm sure you must have all seen structural bolts also. So where do you get to see bolts often other than structures? Is there any place where you get to see bolts frequently?
For the machines,
In where? Sorry.
for the machines and mechanical applications.
Yeah, in mechanical applications, it is often there. In fact, even I'm not able to recall a large quantity of bolts being used anywhere other than construction. Sorry. Anyway, so whenever you need bolts, what else do you need along with the bolt? You cannot use bolts by themselves, right? There is something that always accompanies a bolt. What is it?
Washer.
Washer. Okay, washer comes secondary. Even before washer, you need something.
Nuts.
Nuts. Yeah. So bolts are two component parts, unlike some other connectors. Okay. So bolts require two parts, bolt and the nut, and often you need a washer. Right. Washer is especially required when your bolt hole is slightly too large in comparison to the bolt, and you are afraid that the force transfer will not be very adequate, or there is a chance that the nuts will not be able to get nut or the bolt head, they will not be able to get large enough bearing areas. I will explain to you what bolt head is. Please remind me to talk about the use of washers there when you see the geometry of a bolt. Anyway, so before bolts came along, it's not like bolts were not known at that time, but bolts were not very reliable type of connectors for a very long time. They were considered to be very unreliable because anybody can just unscrew them, open the bolts, right? So that was the major issue, and that's why. And bolts used to get opened very easily on their own. So especially on bridges and all, whenever there is a traffic moving, right, for a long period of time, you will often see that bolts tend to unbolt. So that is the unbolting of the structure. Okay, so that used to be an issue, and bolts also were not very high strength. Plus, cutting off the holes of exact sizes were also relatively difficult. So rivets, the most popular type of connectors for a very, very long time. Okay, and here I have a video for you. So first you see the video, and then I'll talk. You can see my screen, right? You can see the YouTube video. So what you saw here were all rivets. This is how the rivets are kept in one place, and then they are heating one rivet at a time. So they are taking these rivets out from here. So one rivet is placed here. Sorry. So you can see this kind of a rivet sitting here. That is inside a furnace, and they are using a gas torch to heat it. Okay. So they heat the rivet to a very high temperature. Then here they want to install the rivet. So this is a steel plate, and maybe there is a connector here. There is another element that they want to rivet with this big plate. So this person brought this very, very hot rivet, holding it with the tongue, and there is a hole here. In that hole, he places the rivet. And these two people, this person here and that person here, they will be operating a machine, kind of a hammer. This is another second rivet. He's taking it from the furnace, locating it, placing it right at the hole. And then two people come. The other person is providing a restraint to the rivet, and the first person, the person on our side, he is basically using an automatic hammer which is hitting that rivet at a very high frequency for a few seconds, maybe 3-4 seconds, and in that 3 or 4 seconds that rivet changes its shape. So a rivet before it is installed looks like this. After installation, what happens to the shape? So before installation, the rivet has only one head. After installation, it develops another head, which is a result of that high pressure impact energy that is imparted on it. So basically, it had a head and it had a shaft. So I'll talk about this rivet. So this rivet has a head and a shaft, and after heating and hitting it with that hammer, this end also develops into a head, and basically it seals the connection. So basically, rivets are made of mild steel, mild carbon steel. They cannot be very high strength steel, because if the rivet is made of very high strength steel, it will be very difficult to deform it in the desired shape. You are supposed to completely alter the shape of the rivet. Okay, so first you heat it so that it becomes malleable, and then you hammer it under a very high pressure so that it deforms into the desired shape. Now, what happens is that when you install the rivet, at the time rivet is just occupying that space between the two plates. Okay? Later, when the rivet starts to cool down, it starts to shrink. Almost all materials have this thermal expansion coefficient, right? So thermal expansion coefficient is positive, means as it cools down, it starts to shrink. When it shrinks, then these two plates, which were supposed to be, let's say, touching each other, after the rivet starts to shrink, it puts those plates under compression. It kind of squeezes them together under the compressive force from the rivet. So rivet undergoes tension between the two heads. So the two heads are kind of pulling apart, and the shaft of the rivet will be in tension, and these two plates will be under compression. Okay, and as a result of this installation process, what happens is that the rivet diameter will be exactly same as the hole diameter. Why? Because as you are applying all this pressure, the material starts to flow and fills in every gap that is available, right? So even though before the installation, rivet diameter is very small, or significantly small in comparison to the hole diameter. So originally, the hole has to be bigger, so that that person who brings the hot rivet can very easily place it inside the hole. Correct? If you have to fumble, if you have to try and really push the rivet through that hole, it's not possible at that high temperature, right? And sometimes you may have to do these installations at very awkward locations also. So let's say in a real connection, if you see in a bridge, then all these rivets, look at the density of rivets that they had to use. One of the reasons for that was that rivets are not really very strong material. They are made of relatively milder steel. They have low strength, and that's why they had to use so many rivets all over the place. Okay, so initially the diameter is small, but after this hammering, the material flows and occupies all the space that is available. So the diameter of the rivet is same as the diameter of the hole. The technology of rivets, it was very, very popular till almost 1950s, but then suddenly it started to become less popular as more and more developments happen on the bolt side. So I'll talk about what are the advantages and disadvantages of rivets versus bolts are. One major advantage that bolts did not have before is the pre-tensioning of the bolts. Nowadays, the bolts that are used in real structures are mostly pre-tensioned, or they are tightened to a very high level, and they don't unbolt very easily. Another thing is that they are under very high compression. So the other issues that were associated with bolting, I'll talk about them later, those also are taken care of. Rivets are still used not in this kind of a way. So this kind of installation is done at a very high temperatures. These kind of rivets are very uncommon now, unless you are doing also Eiffel Tower. If you see the Eiffel Tower, you have some pictures, search on the internet, look closely, all rivets. Yeah, this major bridge in Kolkata, Howrah Bridge, all rivets. All such kind of old structures, they all are made of rivet. They all use rivets for connections. Nowadays, rivets are not as common. You may see rivets being used in cooking utensils. So you may sometimes see that the handle is attached to the main vessel through some kind of rivets. Sometimes, not always. Also, sometimes you may see blind rivets. So blind rivets are the rivets which can be installed from one side. So you cannot access the other side. See, if you notice here, you need a person on the other side also. Same thing is the limitation of a bolt. When you're installing a bolt, somebody has to be there on the other side also. With welds, that is an advantage that many times you don't need another person on the other side. You can just weld from one side. So that is one advantage with weld, but both rivets and bolts have this disadvantage that other person has to be, the people are required on both sides of the connection. And sometimes that may be very difficult. With the blind rivets, these are not structural rivets. These are sometimes used in furniture. These are sometimes used in utensils. Sometimes things like bicycle and all, they might be used. So these rivets can be installed from one side. Okay? And you can go to the internet and try and search for some blind rivets. I cannot give you an example right now, but you can easily find some examples on the internet. Okay, they are called blind rivets because you don't get to see what is happening inside. So these rivets go into the, so you have a plate, you have a hole, you push the rivet in, and you push the rivet by using some kind of special jack sort of a thing which goes in, and when you pull that jack out, that rivet swells and locks. Okay, so they are not as strong as these rivets, but that is not the purpose also when these blind rivets are used. Moving forward, coming to bolts, because bolts are now the mainstream. Bolts are not, now rivets are not used anymore. Bolts are more mainstream. So bolts are made of three components here, primarily. One is nut, that is secondary. And the first component is the bolt. And if you may imagine, there is a washer. So here what you see is there are two plates. These hashed areas are two plates. One plate here, one plate here. They have a common hole. So there is a hole which is aligned. So both of these plates had a hole which are aligned together. Then you put a bolt through it. So this is the bolt head. Then you have a bolt shank. Then you have threaded portion of the bolt. So after this point, you have threaded portion. The threads are not marked clearly, but you can imagine that this part is the threaded portion of the bolt. Then you have a nut, okay, and in between you may have a washer. Okay? So what does the washer do? Here the washer is not really serving the purpose that it is supposed to, but basically what happens is that sometimes this hole may be slightly too large for the nut or the bolt head. And as a consequence, what may happen is that you may not, so basically this area here provides the bearing resistance. So the tension that you apply or the amount of twisting that you apply to the nut leads to tension, development of tension in the bolt and development of compression in this plate. Now, sometimes what you may find is that, or not only this twisting, when you actually apply the forces, your real life or working stresses or limit state forces, at that time also you may be applying some tension on this bolt. That is, when you apply this tension, all that tension has to be transferred through bearing here. And if there is not enough bearing area available, this may fail. So sometimes they may realize that the bearing area is a bit dicey. They don't have enough bearing area because there is some issue with the bolt diameter. So they may provide a washer, transfer that force more effectively. But it is not necessarily, it's not necessarily used every time. It may always sometimes be useful. Okay. In these two drawings at the bottom, don't pay too much attention to 1.65D, 1.9D, 0.65D, 0.65D, and so on. I'll talk about these later, but these are as per, these I have taken from an international book, from an American book. So these numbers may not necessarily match with Indian standards. So these dimensions, you don't worry, just focus on the parts. This is the total bolt length, out of which there is a shank length and there is a threaded portion, there is a nut, and there is a bolt head. And this is a common way in which you draw a bolt head. Okay. So the bolt diameter is, of course, has to be less than the hole diameter. Why? Because if the bolt diameter is matching exactly with the hole diameter and the two holes are slightly misaligned, or for some reason there is some inaccuracy in this thing, it will be very difficult to push the bolt through the hole. So you always take some factor of safety, and that those factors are given in table number 19, IS 800. Let me see if I have IS 800 here, which we used to have. Search. Table 19. Yes. You can see this table. Here it is giving the nominal size of the fastener, that is the diameter of the fastener, and size of the hole, which is saying size of the hole should be equal to nominal diameter of the fastener plus the clearance. So standard clearance, diameter and width of slot is, so if you have a bolt of diameter 12 to 14, you need to have a clearance of 1 millimeter. That means a 14 millimeter bolt, 14 mm diameter bolt requires a hole of 15 mm. Similarly, if you have 22 mm diameter bolt or 20 mm diameter bolt, you need to keep 2 millimeter extra for the hole. And the purpose for this is to accommodate any misalignments of the hole. So let's say you have one plate and you have another plate on top of it, and both of them are supposed to have holes exactly at the same location, but somehow they are misaligned slightly. Now you are able to adjust the plates. If you align these holes, some other holes misalign. There may be such kind of situations. You may not have complete freedom to move these plates as you wish, and as a result, you have to make some room for this couple of millimeters to adjust for this. Sometimes you may have to go for oversized clearance in diameter. As I mentioned before, getting the holes to match exactly, let's say you are putting 30 holes in two plates. Yeah. So for all the 30 holes to exactly overlap the other 30 holes, and most of these operations are done by hand, even though in a shop, but you have to mark the centers. And when you first mark the center, you bring the drill bit. Keeping the drill bit exactly at the location where you wanted it to be is relatively difficult. You may often have a slip of 0.5 millimeter here or there. And if you accumulate that over a large number of holes, sometimes you may have a misalignment of a few millimeters. So for that, sometimes you are allowed to go for an oversized clearance. So that means your bolt may be 20 mm, but your bolt hole may be 24 mm. Okay, and that is allowed. Sometimes even to accommodate these kind of misfits or some kind of a freedom to move for the two plates, you may also use slots. Okay, so slots are basically, if I may draw again here, if this is the bolt cross section, a bolt hole typically would be like this, just slightly bigger. This was the bolt in between, but a slot will be, this is the bolt, a slot will be like this. Okay, so the slot diameter is fixed, the length can be then you may have short slot or long slot, and clearance in the length of the slot. So that much of clearance is required in the length of the slot, 4 millimeter, 6 millimeter, and so on. So sometimes slots are also used to allow more freedom for the to make space for the bolts to move around, so that you don't have so much of trouble providing the fit. Okay, now please don't go by these values of 1.65, 1.9D here. You need to go to IS 1364. I think I have a screenshot from there. No, this is not that. Okay, so you can search it on this code is available for free on the internet. IS 1364. It gives you each and every single value. It gives you for a bolt of diameter. Diameter is basically that's how you define. You take this D value, that is the classification. So you say M20 bolt, that means this is the 20 mm diameter. Okay, but all other dimensions, such as what is the diameter of this head, the head has two diameters, right? If you take this head, look from the top, it looks like a hexagon. So it looks like a hexagon. So hexagon may have two different dimensions. You may have one dimension, this one, and the other dimension may be this diagonal one. Okay, in that hexagon. So both these dimensions are specified. Similarly, how much is the length of this shank, how much is the length of the thread, what is the thickness of the bolt head, all those are specified in this particular code for each and every bolt. So the codes, these bolts have to follow these standards. Any bolts that are sold in India have to follow these standards. Okay, typically the area of the reduced cross section at the thread level, as you can see that the cross section, net cross section at the thread level is smaller, right? You can see it, right? So the net cross section area the if this is how the threads are, then the other set of threads and the other side of this are like this, and this is how you are connecting them. Okay, so this cross-section area is the net area, right? So if the rupture has to take place of this bolt in tension, if this bolt has to rupture in tension, then this is the cross-section area that matters. And that cross-section area is approximately 78% of the gross cross-section. So gross cross-section area is here, and net cross-section area is here. Yeah, so net cross-section area is approximately 78% of the shank area. Yeah, almost done. So after this slide, we will stop. And there are different grades of steel that you can use for making the bolts. You may have from very low strength, relatively minor application bolts, to you may have up to very high strength, very high grade bolts. Okay. Generally, what happens is that the high strength bolts are the ones that have greater than 800 MPa strength. Typical steel strength is 400 MPa, right? So I'm talking about the bolts that are having more than 800. 410 MPa is regular steel, which is 250 MPa steel. Yield stress is 250, so ultimate stress is 410. The high strength bolts are the ones that have more than 800 MPa strength, and unfinished bolts, black bolts, are usually the ones which is less than 800 MPa ultimate strength. And the bolts are sold in the market with various different names, and it is very confusing. So usually whenever we buy for our research purposes or any serious applications, we always want to ask them to provide the test data. From the test data, you can make out what is the grade of the material. So if they have to know the grade of the material, many times our suppliers don't know what grade bolts these are. They just say high strength bolt, but they don't exactly know the grade. So we ask for the test data, and sometimes their catalogs have their test data, and which explains to us what is the actual strength. Okay, so as you may imagine, I think I should stop now. It's almost 11:56. I have not given you a chance to ask any questions. All right, why don't you guys let me know if you have any questions? Any questions, doubts, discussions you want to have? Anyone? No? Okay, then I think I can stop here today. In the next class, we will start talking about the behavior and what are the properties available. And I want to get into the design part as early as possible. Okay. All right, so if there are no more questions, we'll stop today. Thank you.